the two extremes of the number line sit 0 and infinity. They are opposite of each other but equally strange. Unlike the other numbers, they refuse to follow the usual rules of math, like division and multiplication. Yet they are at the heart of one, if not the most important tool we have to understand and master nature, calculus. Mathematicians and philosophers from multiple continents have spent millennia arguing over what they are, how they work, and why they are so puzzling. This is the first video of a 3-part series dedicated to 0 and infinity. It is an exploration into two concepts that span centuries of history, math and physics, in multiple continents. 0 and infinity have affected religion, intersected with the culture of the countries who have met them, and powered some world-changing innovations. Since 0 and infinity are so distant from all other numbers, they are the edge cases that allow for a special look into theories of the physical world and the abstraction we use to understand it, math itself. It's hard to imagine life without numbers, but there was a time where none existed. It was before the beginning of history, and the first traces of the history of math are told by bits of rock and bone. In Czechoslovakia, in the late 1930s, archaeologist Karl Absalom uncovered a 30,000-year-old wolf bone with 55 notches carved into it, organized in groups of 5. The prehistoric person who made these incisions was counting something, even though we don't know what. At this time, the concept of a number as we think of it today didn't exist, just a concept of quantity. Millennia passed and humanity evolved. We learned to write and we searched for ways to write quantities. To do that, you need symbols, and so numbers were invented. Every civilization had their own unique sets of symbols and rules, and my favorite number system must be the Mayan system, which used elaborate masks. We need a petition to ditch Arabic numerals and go back to Mayan masks, because it does not get any better than this. But the most innovative of any number system was in Babylonia. In their system, the meaning of the symbols they used for numbers changed based on position. This is roughly the same way as modern numbers work. The number 777 is made up of 3 identical symbols, but the first signifies 700, the second 70, and the third 7. This is called a place value system. This system had a problem. Consider the number 302. The first 3 means 300, then 2 to mean 2, but what do you put in between? You must have something there, otherwise you will just get the number 37. So the Babylonians invented a placeholder, a symbol that was just there to make the rest of the system work. This symbol is the inception of the modern number 0. However, it is still a long way off what 0 is today. It wasn't a legitimate number like 5 or 82, just a useful symbol. Now we need to change country. For ancient Greeks, math looked a lot different than what it looks like for us. They had no symbols for operations, no incognita, they used letters as the symbols for numbers, and they didn't write with formulas, but with complete sentences, which had no spaces or punctuation. But the most crucial difference was that their math was based on geometry. They worked with shapes and volumes, not simply with numbers and operations. What we call x to the power of 2 for them is just a square, and x to the power of 3 is just a cube. It made sense then to their mentality to reject 0. After all, can you have a zero-sided shape, or a cube with the volume 0? It's not sure whether it was the lack of 0 that forced mathematicians to rely entirely on geometry, or if it was the reliance on geometry that caused the rejection of the 0. But either way, 0 was frowned upon, and so was infinity. The Greeks had a term for infinity, apeiron. It is a word with the same negative connotation as the word chaos in English: unruliness, anarchy, possibly even danger. One philosopher, Zeno of Elea, would shine a light on the problem with infinity, the reason it was so conceptually dangerous. Consider a race between Achilles, the runner demigod, and a tortoise, where the tortoise has a head start and is 1 meter ahead of Achilles. In half a second, Achilles covered that distance, but in that half a second, the tortoise has run forward a bit more. This continues forever. No matter how much Achilles ran, he can never catch up with the tortoise. No one could find a flaw in Zeno's reasoning, and the paradox remained unsolved for centuries. One of the most important mathematicians of ancient Greece was Pythagoras of Samos, who was not the inventor of the Pythagorean theorem despite the fact that it has his name because it had been known for 1,000 years before him. There were 4 things that Pythagoras could not tolerate: 0, infinity, irrational numbers, and beings. Why? Because they held the power to shatter his perfect doctrine about the harmony of the universe, the interdependence between math, music, nature, and cosmology, and beings because they contained the soul of the dead and eating them would be like eating people. For Pythagoras, all is number, and for the Greeks in general, all numbers are shapes. Pythagoras believed that the connection between numbers and shape is sacred. The universe is a harmonic masterwork of geometrical shapes, and most of all, ratios. Playing music is a mathematical art, and the ratio found in the musical scale is similar to the ratio between the planets, which as they rotate make heavenly music. All that exists is orderly and balanced. Irrational numbers are an ugly truth that does not conform to this vision. Irrationals cannot be expressed as a ratio of two numbers, that is, you cannot write a finite fractions of integers that describe them. When Hippasus of Metapontus, a member of Pythagoras' cult which was based on those principles, revealed the public about irrational, he was allegedly sentenced to death by Pythagoras himself and thrown off a boat. 0 is also a big pain for Pythagoras. What shape could 0 be? A number without its own shape surely cannot have a place in a universe that is purely geometric. And infinity was just as bad as Zeno has shown. How could the universe be orderly and rational if the fastest runner on Earth can never catch up with one of the slowest animals? 0 was battered and ignored in the West. However, it was not so in the East. In India, the attitude towards 0 and infinity was much different. India first learned about the Babylonian system of numbers and about 0 when Alexander the Great marched in the country in the 4th century BC. But unlike the West, India never had a fear of 0 or infinity. The void had an important place in the Hindu religion. The duality of creation and destruction were intermingled in Shiva, the creator and the destroyer of the world. However, Shiva also represented nothingness. Nothingness was where the universe, infinite in extent, came from, and to nothingness it was destined to return. It's from India that the word 0 comes from. The Indian name for 0 was Sunya, meaning empty, and when the Arabs adopted it, they turned the word into Seife. When some Western scholars heard it, they turned it into a Latin-sounding word, Zephyrus, which contains the root of our modern name 0. It was the Indians who invented the ciphers we use today. However, when the Arabs conquered them in the 700s, they adopted those ciphers, and when eventually those were brought to Europe for the first time by Fibonacci in 1200, they were called Arabic ciphers. Possibly the most important mathematical innovation of the Indians was the decoupling of algebra and geometry. They didn't care much about squares and sections of a cone like the Greeks did. They were fine working with numbers on their own. This allowed them to move beyond all conceptions. Where the Greeks had rejected negative numbers as they had no geometrical meaning, the Indians used them freely. And since now it didn't matter anymore that 0 had no shape, finally it was accepted as a true number and given its legitimate place at the beginning of the number line, before 1. It's worth highlighting here what a seismic shift in mentality it took to accept 0 as a number. It required abandoning a literal, physical, geometric view of the world to adopt an abstract, metaphysical, algebraic view. This allows for massive gains in the reach of your reasoning, but at the cost of your grasp with the real world, with reality. Algebra is the offer made by the devil to the mathematician. The devil says, I will give you this powerful machine and it will answer any question you like. All you need to do is give me your soul. Give up geometry and you will have this marvelous machine. The danger to our soul is there, because when you pass over into algebraic calculation, essentially you stop thinking. You stop thinking geometrically, you stop thinking about the meaning. But it is a deal that must be paid. There is only so much you can learn from staring at squares and circles. At some point, humanity had to leave the cozy nest of geometry to venture into the cold, strange land of abstract mathematics. 0 and infinity, despite being quite literally opposite to one another, have a surprising similarity. They have unusual mathematical properties that no other number has. The axiom of Archimedes dictates that if you add a number to itself enough times, it will exceed any other number in magnitude. 0 violates this axiom. No matter how many times you add 0 to itself, you will always get a 0. It also refuses to make any other number bigger or smaller. It's like it has no substance. like it's not really a number but the ghost of a number, harmless and unable to affect anything. Infinity does the opposite. What is infinity plus infinity? Infinity again. But why exactly? It will also make sense to say that it makes two infinities, even though that's not the case. We will actually talk much more in depth about operations with infinity in the next video of the series. When it comes to multiplication, 0 has again a very strange behavior. Any number multiplied by 0 becomes 0. From a ghost of a number, it becomes a hydraulic press that crushes every other number into nothingness. The same goes for infinity, but in the opposite sense. Multiply a number by infinity and it blows out of proportion until it becomes infinity itself. Division is even stranger than that. If 10 over 2 is 5, then it's also true that 5 by 2 is 10. So to say that 5 divided by 0 equals x, where x is a non-zero number, we are saying that x multiplied by 0 is 5. But we know that multiplying any number by 0 gives you 0, so this equation is nonsensical unless 5 equals 0, which is not true. And if you try to divide any number by infinity, well, it would make sense to try this reasoning. If you take any number and divide it into an infinite number of parts, the parts will be 0, right? Sort of. We don't have all the tools we need to do this at this point in the story, but 0 is a reasonable guess for now. It seems that in the realm of multiplication and division, any number which comes in contact with 0 and infinity loses itself and morphs into one of the two beasts, either 0 or infinity. The two seem to be like two whirlpools, dragging every other number who swim too close down to the bottom, where only 0 and infinity remain. It is now the European Middle Ages, and the Church is the institution which counts as its members the most educated thinkers of society. The Christian culture, faith, and teachings is founded on two columns, the Semitic Bible and the Greek culture. But when theologians started examining both in details, contradictions started popping up. One was fearful of 0 and infinity, and the other was the opposite. For example, Aristotle, the main Greek philosopher studied by the Church, said that the universe has always existed in a hypothetical and potential infinity, while the Bible declared that God had created the world out of the void. So theologians try to come up with ways to make the two views agree with each other, with sometimes awkward results. For example, when one hypothesis as to where the world actually comes from, theologians try to claim that when the Bible said the world was created out of nothing, it didn't mean absolute nothingness, but a nothing something, so that in a sense both the Bible and Aristotle would be correct. But medieval Christians had opinions of their own on 0 and infinity, and they actually argued quite a lot about it. A popular view at the point was to accept the view that infinity does not exist, except for a watered down and pretty confusing version of infinity that Aristotle had created to try and get around Zeno's paradox. A few theologians, though, went against the current. One of them was St. Augustine. He thought that not only infinity existed, but that God himself was infinite, and that he could deal with and contain infinity. If numbers are an unlimited amount, infinite, would it not be heresy to think that an all-powerful God only knew numbers up to a certain size and was ignorant of all the others? Most other important theologians, such as Thomas Aquinas, pull back from these ideas though. They believed that while there was some connection between God and infinity, he could not really deal with infinity because such a thing did not exist at all. It would be like asking whether God could imagine a square circle. He cannot, not by any fault of his own, but because such a circle does not exist and cannot exist. But for medieval scholars, the void had a particularly dark connection. Boethius made this argument. God is omnipotent, so there is nothing he cannot do, but he is also the infinite goodness, so the only thing he cannot do is evil. Therefore, evil is nothing, and Satan, evil incarnate, is 0 itself. The mathematical symbol for infinity, called the lemniscate, was invented by the English mathematician John Wallis in 1655. In one of his writings, he just casually wrote, let the symbol denote infinity, and then continued on with his calculations. Since he didn't explain how he came up with the symbols, we only have speculations. Maybe it came from the old Roman sign for 1,000, which was later replaced by M, or maybe it is a variant of the small Greek letter omega, or maybe it's just an infinite loop. We can only guess. Infinity now had its own notation, but the concept itself was still far from welcome. I protest against the use of an infinite quantity as an actual entity. This is never allowed in mathematics. The infinite is only a manner of speaking, in which one properly speaks of limits to which certain ratios can come as near as desired, while others are permitted to increase without bound. But this attitude was to change, as infinity proved to be crucial in one of the most important discoveries of math. Archimedes, back in ancient Greek, was the first mathematician to come so close to discovering calculus without actually inventing it. One important problem for the Greeks was the sections of a cone. If you take a cone and slice it, depending on how you angle the cut, you get a circle, an ellipsis, a parabola, or hyperbolas. He wanted to understand the area of a parabola, which was a problem that stumped the Greeks. To do so, he used a trick. He drew a triangle inside the parabola. The area of a triangle, unlike that of a parabola, is easy to measure, so that gave him an idea of what the area was. And then, in the gaps left, he inscribed 2 more triangles. This left 4 gaps, which he filled with more triangles. If he could repeat this process an arbitrarily large number of times, he could know precisely what the area of the parabola is. This is the principle behind integral calculus. However, the true development of calculus was still a couple millennia away. Kepler, the same guy who discovered the basic rules behind planetary motion, spent the year of 1612 gazing into wine barrels, because he had noticed that windmakers and coopers used a very rudimentary method to measure the area of the barrel, and he wanted to find a better way. To illustrate his reasoning, let's consider a triangle, one with height and base of 8, so an area of 32. Kepler imagined inscribing a rectangle inside it. The first time it will be a square with sides 4, yielding an area of 16, pretty distant from the original area. But if you make the rectangles smaller and add more of them, the situation changes. Add 3 rectangles and you get 24. Add 7 and you get 28. As the thickness of the triangles get closer to 0, the sum of their areas get closer to the area of the triangle. Kepler applied the same reasoning to wine barrels, slicing them up to infinitely tiny pieces and adding them back together to yield their volume. The other half of calculus, differentiation, was the product of Newton and Leibniz, who discovered it pretty much independently and then spent a great deal of time arguing over who should get the merit for the invention. Newton's style of differentiation doesn't look like the one we see today. It was based on fluxions. Leibniz also developed his own system of differentiation, and his was more similar to ours, since he used the dx notation. Both of them had the same problem. Their system required a division 0 over 0, which as we've seen is undefined, and so it was almost a matter of fate to believe that this was the correct process. However, despite the process they used not having all the rigor mathematics need, their calculations were right, and so mathematicians of the time had to live with the fact that they had a process that gave correct answers, despite not knowing how or why. In calculus classes, the limit is the first concept that is taught, but historically it was the last to be invented. D'Alembert is best known for his collaboration on the Encyclopedia of Human Knowledge, but he was also the man who solved the calculus problems with 0. Remember the Achilles and the tortoise paradox? They both are getting closer and closer to the 2-meter mark. D'Alembert realized that the ultimate destination of the race is the 2-meter mark. No step they take brings them further away or keeps them at the same distance. The 2-meter mark is the limit of the race. It's a very subtle change in notation, but it makes all the difference in the world. When you have an infinity in an expression, or when you divide by 0, all the mathematical operations, even those as simple as addition, subtraction, multiplication, and division, go out the window. Nothing makes sense any longer. However, by putting these limit signs in front of the series, you separate the process from the goal. In this way, you avoid manipulating infinities and zeros. Just as Achilles subraces are each finite, each partial sum in a limit is finite. You can add them up, divide them, square them, you can do whatever you want. The rules of mathematics still work, since everything is finite. Then, after all your manipulations are complete, you take the limit. You extrapolate and figure out where the expression is headed. Visually, this is fundamental logic behind limits. Take a curved line. If you zoom on it far enough, it will look more and more like a straight line, and at a certain scale, it will act like a straight line as well. Since working with straight lines is much easier than working with curved lines, this change in perspective simplifies the problem. D'Alembert informally invented the limit, and Agustin Cauchy, Bernard Bolzano, and Carl Weierstrass later formalized it. At this point, calculus has finally taken shape. Its two major pieces, integration and differentiation, and its heart, the limit, are well established and cherished, since their use expands mankind's ability to understand and manipulate nature by working with zero and infinity. We went a long way from the past where those two concepts were just arguments for philosophers and rejected by mathematicians. It was now clear that they were indispensable to create one of the most important discoveries ever in math. But there's still a piece of the puzzle that's missing. How are zero and infinity connected? Why do they seem to share so many properties and behaviors despite being opposites? There are a couple of things we need to know before we can get there. Gaspard Monge was a geometer specializing in 3D geometry, which is extremely useful to draw architecture and engineering projects. So useful, in fact, that much of it had been made a state secret by the revolutionary government and the Napoleonic government that succeeded it. The French Jean-Victor Poncelet was a student of Monge and worked as an engineer for Napoleon's army, but he had the misfortune of participating in the disastrous 1812 French invasion of Russia. At the Battle of Krasnoy, he was left for dead on the battlefield and captured by the Russians, and it was in the Russian prison that he founded a new discipline, projective geometry. Projective geometry deals with the relationship between geometric figures and the image that results when you project them on another surface. Consider a single point in space, an object laying on a plane and a vertical plane. Now, from every point of the object, draw a line that arrives at a single point. Those lines go through a vertical plane and create an image. This process is called mapping. This concept will be useful in a minute, but there's another thing before that. Despite the name, imaginary numbers are just as real or as fake as any other type of number. They're not of everyday use, unlike, say, fractions or whole numbers, because they help solve a very specific problem, taking the root of a negative number. Equations like these are easy to solve. The solutions are 3 and minus 3. But what about these? Adding the minus sign changes everything. How could you take the square root of a number that's less than 0? Let's take a simple expression, x to the power of 2 equals 9. We know that if we multiply anything by 1, nothing changes, so we can turn the expression into 1 by x to the power of 2 equals 9. Now, we know that raising a number to the second power is the same as multiplying the number by itself, so the expression becomes 1 by x equals 9. The trick here is that we think of x not just as a number, but as a transformation. Think of this problem as a saying. If we are on the number line and we start at 1, and we want to arrive at 9 through 2 operations, symbolized by the 2 x's, how do we do that? Well, first we need to scale up by a factor of 3, or of minus 3, and then scale it up by 3, or minus 3. That's why 3 and minus 3 were the solutions. Now let's go back to x to the power of 2 equals minus 1. That's like saying which operation when applied twice brings us from 1 to minus 1, a rotation of 90 degrees. And if we want to go from minus 1 to 1, we can again rotate in the same direction twice. And this is what imaginary numbers are. Notice that we've started from a one-dimensional line, and by rotating, we have created a second dimension. If we take the number line as the x-axis and this other vertical line as the y-axis, we've made a complex plane, created in the 1830s by the German mathematician Friedrich Gauss. Imaginary numbers are made up of two parts, a real part and an imaginary part. The real part is made up of real numbers, integers, fractions, or irrationals, and is found in the real axis, and the imaginary part is found in the imaginary axis. So for example, the number 5 plus 2i would be here, the number 3 plus 3i here, and so on. Why have we talked about projective geometry and imaginary numbers? Because they are the two puzzle pieces we need to finally understand zero and infinity. Let's put the pieces together. Let's bring back the complex plane, with imaginary numbers on the y-axis and real numbers on the x-axis, and let's lay it down. From the point 0, the origin of the plane, let's create a sphere. Choose a point P on the plane and draw a line from it to the North Pole. It will intersect the sphere at the point projected P. So we say that projected P is the stereographic projection of P from the complex plane to the sphere, and vice versa, P is a stereographic projection of projected P. Repeat this process with every single point on the complex plane. Now, every point on the plane is mapped by a point on the sphere. Both the sphere and the plane contain every complex number possible. There is only one point on the sphere that doesn't have a number, the North Pole, where all the projections start. The South Pole, where the sphere sits, is equal to 0, but what number is the other pole equal to? Let's choose a few points on the plane that are increasingly further away from the sphere. Look where the projection lands. The further away a point on the plane is, the closer to the North Pole its projection gets. A huge number that is extremely far from the sphere will project a point that is very, very close to the North Pole, and if we consider a number infinitely large that is infinitely far away from the sphere, then it will project itself exactly on the North Pole. So, the North Pole is the projection of infinity. This is the Riemann sphere. We have a plane containing every complex number and a sphere containing every complex number plus 1, infinity, which sits at the North Pole, while the South Pole is equal to 0. We now have a model to visualize every number. Now, what happens if instead of considering the stereographic projection of one single point, we consider the projection of groups of points? Say, for example, the circumference of the sphere. It projects a circle onto the plane. And if we take other circles, they all project a circle on the plane. That is, unless the circle goes through the North Pole, in which case the projection is not a circle anymore, it's a line. Why? Let's go back to what we said about limits earlier. If you take a curved line, for example a circle, and you zoom in far enough, it will look like and act like a straight line. From this, we can do the opposite reasoning and say that any straight line can be thought of as a part of a circle with an infinitely large radius. When the radius tends to infinity, we are left with a line. If you want to see it for yourself, take a flashlight and point it straight at a wall. It will project a circle. But if you tilt the flashlight, the shape it projects will change. It will become an ellipse. And as you tilt it more, it will stretch to eventually become a parabola. The more you tilt it, the more it will start to look like a straight line. So a line can be viewed as a circle with infinite radius. In the Riemann sphere, this becomes a fact. A circle passing through the North Pole, aka with a radius of infinity, projects a line onto the plane. But the two poles can actually switch places. In the Riemann sphere, 1 over 0 equals infinity and 1 over infinity equals 0. So if instead of x we take 1 over x, then we get that the South Pole is equal to 1 over 0, which is infinity, and the North Pole is equal to 1 over infinity, which is 0. The sphere gets flipped upside down. But the most important part comes now. Let's put the poles back on their original values, and let's take two numbers, say 1 over 2 and 2i. Square them, cube them, raise them to the 4th power, to the 5th power, and so on and on. 2i spirals upward to infinity, while 1 over 2 spirals downward to 0. This is true for every number. Once you start dividing and multiplying it, they spiral inexorably to one of the two poles. The only numbers that escape this fate are the ones that are equally distant from the two rivals, like 1, I, minus 1, and minus I. The Riemann sphere visualizes two intuitions about 0 and infinity, that they have a special place among all other numbers, which in the sphere is represented by the fact that they are at the poles, that they share equal and opposite properties, which is represented by the fact that they can switch places, and that every number, once you start multiplying and dividing it, is dragged to one or the other like an inescapable whirlpool. We've arrived at the end of the first part of our journey through 0 and infinity. We've covered a lot of ground: history, calculus, projective geometry, and some complex analysis. Get ready to cover even more ground, because the next part will be dedicated exclusively to infinity. We'll meet angels playing infinite horns, hotels with endless rooms, and the strange fact that infinities come in different sizes, and some of them as big as 0. Until then, be well.